Unit 9A deals with electric charge and the electric force. The effects of electricity were first noticed by the ancient Greeks, who realized that when polishing amber stones with silk, that the stones would attract straw. This attraction is due to the force that electrically charged objects feel. So what happens in this process is when the silk rubs up against the amber strips away electrons from the silk because it is more electronegative. This means that there's an overall negative charge on the stone of amber and a positive charge on the piece of silk. And throughout this process, only electrons were transferred back and forth between these objects, but the same total amount of charge is constant throughout this entire process. And we call that the law of conservation of charge. Just like mass is conserved and energy is conserved, charge is also conserved. So every time that we're talking about electricity, really we are talking about electric charge. And the variable for charge is Q. Sometimes it'll be capitalized, sometimes it will be lowercase, but Q stands for charge. And charge ultimately is carried by electrons. Charge has units of coulombs, and one electron has a charge of 1.6 times 10 to the negative 19 coulombs. This value right here we call the elementary charge value. But of course for electrons, they would have a charge of negative 1.6 times 10 to the negative 19 coulombs. Charge can only ever be positive or negative, and for two objects that have the same charge, positive and positive or negative and negative, those objects will repel each other. They'll push away from each other. But for objects that have opposite charges, positive and negative, those objects would be attracted to each other. So here, this piece of silk is negatively charged and the glass rod is positively charged, and that's why the glass rod is attracted to the piece of silk and the silk is attracted to the glass rod. You can see examples of repulsion here in B and C. So if these charged objects are feeling attraction or repulsion, really we would say that they're feeling a force. This force is called the electric force, or often it will be called the electrostatic force, and this exists between any two charged objects. Just like all forces in Physics 1, the electric force has units of newtons. And our formula for the electric force is shown here, where force is a vector. It can point in a specific direction, and that depends on the arrangement of your charges. If it will be pulled left or right depends on if it'll be attracted or repelled. And in this formula we have a constant called Coulomb's constant. The value is listed here, 9 times 10 to the 9th, and it has some pretty unique units with it as well. Newtons times meters squared over Coulomb squared. And then Q1 and Q2 are the charges of both objects involved in the electric force, and R is the distance that separates those objects. So here we have two negatively charged objects, Q1 and Q2, separated by a distance R, and since they're both negative, they will be pushed away from each other. So the force of particle 1 on particle 2 is shown here, pushing it to the right, and the force of particle 2 on particle 1 is shown here, pushing the first particle to the left. Of course, these forces will be equal and opposite as according to Newton's third law. And if we have multiple forces acting from multiple charged objects, we would set up a sum of forces according to vector addition rules. So here, if we're thinking about the forces that are acting on particle 2, it would be pushed to the right by particle 1, and it would also be pushed upward by particle 3, and we could add together those two vector components to get us the overall resultant vector for the total electric force felt by particle 2. So in general, this is a unit that will call back to some of the things that we've learned in Physics 1, especially relating to forces. So you might want to refresh yourself on the different forces that we dealt with in Physics 1. Those are shown here. Or you could take a look at the video shared up at the top of the screen right now if you want to take a look at the review of this content earlier in the playlist. Also, since we're dealing with forces, we'll have to remember how to draw free body diagrams or force diagrams. Some examples are shown here, and that will also be shown in the previous YouTube video as well. So there are certain objects that allow charge to move freely within them, and there are certain objects that prevent charge from moving freely within them. We call these conductors and insulators respectively. Conductors allow electric charge to flow freely within them because there are electrons that are not tightly bound to the atoms within that material. The electrons are considered free electrons. They can move throughout the material. And in general, conductors have very low resistance. So we're talking about metals, we're talking about water, or wires. Things like that are good conductors. Insulators do not allow electric charge to flow freely within them, and that's because electrons are tightly bound to the atoms that constitute the material. Insulators have very high resistance, so some examples of these might be like rubber or wood or paper. These objects are insulators because they do not allow electric charge to be transferred within them. So our new diagrammatic model for this unit is called a charge distribution diagram. It basically represents the imbalance of charge within a material. So let's take a look at how to draw these. Basically, you will draw positive and negative signs on the objects based on where the charges reside. For an insulator, you'll want to draw these charges bound together with another positive charge in a little pocket like you see here. So every positive charge will have a negative charge, but you can allow for those positive and negative charges to lean one way or the other. In this case, for part A in this insulator, the negative charges are leaning to the left because they are attracted to this positively charged rod, and the positive charges in the insulator are leaning to the right away from the positively charged rod because those feel repulsion. But since it's an insulator, those charges are not free to go all the way to the right or all the way to the left. They kind of stay bound to their local site where they started. We call this leaning of the charges polarizing the material. That means that the electrons have a certain shift in one direction, but they are still in their original location. However, if you have a conductor, that means that the charges are free to move within the conductor. So here, when we bring a negatively charged rod near the conductor, you'll see that the electrons will move away from the negative rod. They'll be repelled, they'll go to the right side, and that will leave an absence of electrons or a net positive charge on the left side of the conductor here. So here's an example of a charge distribution diagram that you might want to look through on your own time. This is in the OpenStax textbook. Here's another charge distribution diagram of an electroscope, an object that's used to measure the amount of charge in a material. And here's a charge distribution diagram for a Van de Graaff generator, which is like a large metal sphere that you can use to generate charge. So in general, charge distribution diagrams are a relatively simple type of diagram where you basically identify where positive and negative charges are within an object. A field is a way of mapping out the forces that would be felt by an object within that field. So we have examples of fields like the gravitational field of the sun or Earth. Those are fields in physics. But another type of field that we have in physics class is an electric field. Any charged object will have an electric field extending from it throughout all of space that will exert a force on other charged objects within the field. And so, if we just take that force equation that we originally had and we remove one of the charges, we get a new equation for the electric field generated by just one charge off on its own in space. So, to formalize the equation a little bit, capital Q here represents a point charge, just one place in space where we have a charged object and an electric field emanates from that point charge. Lowercase q is a test charge. It's the charge that feels the force from the point charge. So in this equation for the electric field, capital Q is used because that's the point charge that generates the electric field. In this equation for electric field, lowercase q, the test charge, is being divided out from the original electric force that was felt. So we're going to cover more about the electric field in our next unit, but you can begin thinking about this as a way of visualizing the forces that will be felt by charged objects. That'll cover everything for Unit 9A. I'll see you in the next one.